Anomeric effect. This is also called Edwards-Lemaitre effect. The term anomeric effect was introduced in 1958. This effect was originally observed in pyranose rings by J.T. Edward in 1955 while studying carbohydrate chemistry. The anomeric effect is most often observed with oxygen but can also be seen with other lone pair bearing heteroatoms in the ring, such as nitrogen, sulfur, and phosphorus. The preference for the axial position by an electronegative substituent such as alkoxy or acyloxy group bounded to the anomeric carbon is called the anomeric effect. For example, when D-glucose reacts with methanol in the presence of HCl to form a glucoside, the major product is methyl alpha D glucopyranoside with the OCH3 on C1 at the axial position, and the minor product is the methyl beta D glucopyranoside with the OCH3 group on the C1 at the equatorial position. This indicates that the alpha glucoside is thermodynamically more stable than the beta glucoside. Although conformationally, the beta anomer should be more stable. Now see, this is the structure of methyl alpha D glucopyranoside, where this OCH3 group is in the axial position. This is becoming more stable. And here, in case of methyl beta D glucopyranoside, this OCH3 is in the equatorial, and this is the less stable. You can say that their oxygen's lone pairs are actually there is some repulsion between these lone pairs. Actually, there are some beautiful logic behind this phenomenon. The first point is repulsion between non-bonding electrons. The dipoles associated with the non-bonding electrons of the alkoxy group at C1 and the non-bonding electrons on the oxygen atom of the ring repel each other when the alkoxy is in the equatorial position. That means these two lone pairs are repulsing each other. They are further apart when the alkoxy group is in the axial position. Because of this repulsive dipole-dipole interaction, the beta anomer is thermodynamically less stable than the alpha anomer, and as a consequence, the alpha anomer is obtained as the major product. This is one reason. Another one is the hyperconjugation. A widely accepted explanation is that there is a stabilizing interaction, which is the hyperconjugation, between the unshared electron pair on the heteroatom, the endocyclic one in a sugar ring, and the sigma star orbital for the axial CX bond. That means there is some hyperconjugation from this oxygen lone pair to the sigma star of this carbon and oxygen. This causes the molecule to align the donating lone pair of electrons anti-parallel to the sigma star orbital, lowering the overall energy of the system and causing more stability. That means this orbital and this CX bond is in anti-parallel position, which gives a more chance for the overlap. In case of this one, in case of this beta position, this is not anti-parallel. Here is sigma star and this one is the lone pair. These two are not anti-parallel. Even this one is also not anti-parallel with this. This cannot overlap. Another one reason is dipole minimization. Another explanation for the anomeric effect is the equatorial configuration has the dipoles involving both heteroatoms partially aligned and therefore repelling each other. By contrast, the axial configuration has these dipoles roughly opposing, thus representing a more stable and lower energy state. as the dipole, this one and this one, is almost opposing each other. That's why this structure is more stable. But this dipole has a direction in this one is this. These dipoles vectors are repelling each other. They can repel. Now come to some effects. The first one is substitution effect or the substituent effect. When X, where X is the exocyclic group, is OH or CN, the equatorial position is preferred on the cyclohexane ring, but the axial position is preferred on the tetrahydropyran ring. That means if this is just a cyclohexane ring, this like this, then the equatorial position is preferred, this one. But if that is a tetrahydropyran ring, that means, oh, what is happening here? Oh, this one will be oxygen. If like a tetrahydropyran ring, then the axial position will be preferred. And this is X. When X is equal to fluorine, the anomeric effect is in fact observed for both rings. In case of fluorine, here in case of cyclohexane ring, fluorine will adopt the axial position. And in case of NH2, the no anomeric effect stabilization is observed for, and both systems prefer the equatorial position. If the X is NH2, then in both case, that in case of cyclohexane and in case of tetrahydrofuran ring, in both case NH2 will adopt this this equatorial position. This is because of both steric and reverse anomeric effect. So we will learn what is the reverse anomeric effect after 1-2 minutes. Now see the solvent effect. A polar solvent with a high dielectric constant decreases the dipole-dipole repulsive interactions. The anomeric effect weakens as the polarity of the solvent increases, and as a result, the equilibrium is shifted in the direction of the conformationally more stable beta anomer. In a relatively less polar solvent such as methanol, the anomeric effect becomes much strong, and as a result, the amount of the alpha anomer increases. In fact, there is 50% of alpha D glucose in dry methanol. For a substituted tetrahydropyran, when X is equal to a fluorine, the anomeric effect was observed in both media. In the gas phase, that is with no solvent, and in aqueous solution, that is with polar solvent, the axial position was always preferred in case of fluorine. This is attributed to hyperconjugation. When X is OH hydroxyl group or CN, the anomeric effect was seen in the gas phase when the axial position was preferred. However, in aqueous solution, substituents prefers the equatorial position. So in one case the substituents are preferring axial, and in case of aqueous solution the substituents are preferring equatorial position. But in case of NH2 group, no anomeric effect was observed and the equatorial position was always preferred. Some other factors. A substituent is more stable in the equatorial position because there is less steric strain in that position. The OH group bounded to the anomeric carbon is in the equatorial position in beta D glucopyranose, whereas it is in the axial position in alpha D glucopyranose. Again, the anomeric effect is outweighed by other factors such as an equatorial OH group is less crowded and better solvated by water than an axial one. This effect stabilizes the beta pyranose form in aqueous solution. Also, the attractive interaction of the hydrogen of the anomeric OH group with the lone pair electrons of the ring oxygen decreases the importance of the anomeric effect, making beta D glucopyranose more stable than the alpha anomer. For these reasons, beta-D-glucopyranose predominates at equilibrium in an aqueous solution. Now, reverse anomeric effect. It refers to the apparent preference of positively charged nitrogen substituents for the equatorial conformation beyond what normal steric interactions would predict in rings containing an electronegative atom, such as oxygen. Substituents containing carbons with partial positive charges are not seen to exhibit the same effect. So what is happening in case of reverse anomeric effect? The substituent is preferring to be in the equatorial position. The pyridinium substituent strongly prefers the equatorial position, as steric factors would predict. That means it prefers more than the steric factors can predict, okay? But actually shows a stronger preference for this conformation than predicted, suggesting the reverse anomeric effect is contributing. So in case of this pyridinium type of salt, the reverse anomeric effect is much more pronounced.